So what we find is that these efficiency maps are quite time consuming. And this is a case study we did with a partner company to really compare us with a competitor. And we took a very low density efficiency map, 200 points per map, which we're seeing a lot of the auto manufacturers do 1,000 to 4,000 points per map. So this is very low density. We took 5 temperatures and 5 states of charge, which resulted in 200 points per map times 5 temperatures times 5 battery voltage equals 5,000 measurement points. We had the test stand transitions, we had heating up and cooling down. We actually did not account for the other transient calibration retesting. And what we find is that for this 200 points per map, or 25 maps, 10 seconds per measurement point took about 70.5 hours. With 1 second per point, with our eDrive system, it's about 13 hours. And I apologize for this being in US dollars, but that equates to about 17,000 US dollars if you were testing at an external test house. And what we find is that the longest delays are really in that heating up and cooling down, keeping in that temperature range. So by testing more quickly, you can actually test more quickly because you're not spending as much time heating up and cooling down, because you spend less time at each operating point. But this is really to demonstrate that this is quite a time-consuming test. HVK is very good at helping you accelerate this. How do we do that? So we do that acceleration with a technology we call cycle detect. So in our cycle detect, in our measurement system, we have a real-time digital signal processor where we do all of our calculations in hard real time. And in that digital signal processor, we have a function where we track fundamental frequency. Now, fundamental frequency in the current is proportionate to speed. We identify zero crossings. We take 2 consecutive zero crossings, and we have this square wave that indicates our averaging period. For those of you who are not familiar with electric power, you need to do your calculations on a even number of half cycles to get an accurate measurement. It comes down to the symmetry. So we take all of our points, we calculate our RMS, our power, our efficiency. This one prevents us from needing a settling time. We don't have to wait for an instrument to lock onto a frequency, constantly tracking the frequency. So we can move very quickly. Rather than 10 seconds, we can test in 1 second, half a second, 1/10 of a second, or faster. We can also average as many together as you want, so you can account for maybe an instability in your control. But this allows us to test very quickly. As we'll see in a moment, it allows for some other things as well. But this cycle detect is key to what we're very good at, which is testing fast. And as an example of how that helps us test fast, if we look at a traditional fixed time method, let's say we need to measure for 1 second per measurement point. Well, at low speed, our 1 second gets us a couple of rotations. As we increase speed, we get a couple more rotations, but we're always measuring for that fixed time period. This is just measurement. This is not transitions. Now, if we do a cycle basis, let's say we measure 1 cycle. Well, at low speeds, this might take a little longer. But as we increase speed, we can actually test more quickly. At high speeds, we can significantly reduce our test time. And rather than a fixed 1 second, or realistically with some competitors, 10 seconds, now taking a fraction of a second, we can significantly reduce that test time because we only need 1 or however many cycles you choose. So we can reduce the test time by using this cycle basis. We can really test as fast as your dynamometer can go. Now, if we extend this cycle basis to its natural conclusion, we get something very interesting.